Okay, so I mentioned that maybe if we put some numbers in there, maybe this will make more sense to us. So here's a differential, set up autonomous because it's only one singular variable. So let's see if we can find our critical points about this. The only thing we have is that factored form. So y minus 1 equals 0, which means we only have one critical point. So we only have the point 1 on our number line. Okay, so what's happening? So going up and going down. Okay, so that means our we're broken up into two regions. We have anything before 1, and we have anything from 1 to infinity. Okay, so let's, sorry, y minus 1 squared. Now, oddly enough, because it's squared, does it really matter what we plug into that? Because if I plug in a negative number for y, I'm going to get a negative number on the inside of the parentheses. So if I square that, I'm going to get a positive thing, right? So that means it's, with negative values, it's increasing. And if I plug in something bigger than 1, I get something positive. So something positive squared is still something positive. So that means I get something positive there. Okay, so now we've got arrows going different directions. Let's jump and look at what does that mean? Okay, so suppose we have a non-constant solution of an autonomous differential equation, and C is a critical point. There's really three behaviors that we could see from those phase descriptions. So draw my little number line here. There's my solution. So I could see something where it's going towards the constant. And we will refer to that behavior as what's called an attractor. And we also then would describe that as asymmetrically stable, meaning if you pick any point near that region, it's going to approach that constant. Okay, so what about this one then? So again, take our critical point. This time I'm going to have my phase go away from that critical point, right? And so that one we call a repeller. When it's, no matter where you put it, it's trying to go away from that solution point. And we refer to this, that critical point as an unstable critical point or a repeller. For obvious reasons, that looks like it's repelling the solutions away from it. So we mentioned there's a third case. This third case is the semi-stable case. And it's essentially a combination of the two. So I'm going to draw two pictures here. And one of them has them go towards point C and then away from point C. And then the other one has it, this part is going away and this part is coming towards. So whenever we see that one, we refer to that as a semi-stable direction field around those solutions. Okay, so this next part is sort of an interesting property about autonomous differential equations and direction fields related to them. So before I get to what's interesting about that, let's actually go get a picture of this. So dy dx equals 2y times y minus 1. So let's jump over to our resource and type that in. Okay, so 2 parentheses y minus 1. Okay, so we get a nice pretty picture like that. And I would say just kind of keep that snapshot handy. I'm going to show another graphic and kind of get to what the property is for these particular differential equations. But let me jump over to the notes. Okay, so if a first order differential equation is autonomous, then we see from the far right side of its normal form that the slopes of the lineal elements through points in the rectangular grid used to construct it depends solely on the y-coordinate. Put another way, lineal elements passed through the points on any horizontal line must have the same slope and therefore are parallel slopes along any vertical line will vary, of course. Okay, so let's go back to our picture, and let's specifically look and see, do we notice anything horizontally and anything vertically? So let me run back to our image. And if you notice, as far as going across horizontally, they're all parallel lines to each other. Those are all parallel slopes. So the entire picture is full of those. And that is just a unique characteristic of autonomous differential equations, that they all have that nice, pretty, nice pattern to it. So horizontally, you see that pattern. Vertically, you don't. Vertically, it changes over time. But there you go.